Ix plus Iy plus I1 is 0. Right? Because Ix is moving out, I1 is moving out, Iy is moving out. So Ix, Iy, I1, everything added up, that should be equal to the total amount of current moving into V1, and then there is no current moving into that node 1. So we have Ix plus Iy plus I1 is equal to 0. So if we have that, so you can write down V1 minus 10 divided by 1, then V1 by 7 plus V1 by 10 is equal to 0, right? Because Ix is nothing but V1, the potential is V1 minus 10 volts divided by the resistance between them. I1 is V1 minus the ground potential. So there is the ground potential, which is 0. So V1 minus 0 divided by 10. And Iy is V1 minus the ground potential divided by 2 plus 5, 7. So I have this. So if I get this equation. So if I take this and if I solve for this, eventually I will get V1 is equal to 700 by 87 volts. Okay. So then what is I1? I1 would be just V1 divided by 10, right? So I1 is V1 by 10. So I have 700 divided by 870. Okay, so this is my I1. And then I need to find I2 now. So when I'm trying to find I2, what I have to do is I have to remove the voltage source by short circuiting it. So find I2 now. What was I2? I2 is something where you no longer have the voltage source. So here there was a voltage source before, but I just removed it. So I'm just short circuiting it. So this is 10 ohms. There is a current I2 flowing. There is a 2 ohms resistor. There is a 4 ampere current. Let's call it V3. This point, let's call it node 2. Then there is a 5 ohm resistor. Okay, so this is what we have. This is the circuit. So we have the voltage current source intact now, but the voltage source over here, that is gone. So there is no voltage source. So now I need to find out what I2 is, what the current I2 is. So for that, what I do is I'll just call this node 2 as before and call this node 3. So now what will be the KCL at node 2? So KCL at node 2. The KCL at node 2 would be V2 divided by 1. So the V2, the current flowing to the 1 ohm resistor from V2 towards the ground, plus V2 divided by 10, which is the current flowing through, which is just the current I2, that is the current flowing through the 10 ohm resistor from V2 towards the ground, plus V2 minus V3 divided by 2. So that is the current flowing through this 2 ohm resistor. Okay, so that current is nothing but the potential difference between the resistor divided by the resistance. So I'm saying that the current is flowing from left to right. That's why I am putting V2 minus V3. So I'm saying that V2 is at a higher potential. So that's the assumption. Eventually, if that is wrong, I'm going to get some negative signs, as I have been saying many times before. Okay, so we get that, and then we solve for these things. So 10 V2 plus V2 plus 5 V2 minus 5 V3. That would be 0. And then that actually tells you that V2 is 5 by 16 V3. So you can write V2 in terms of V3 or V3 in terms of V2. Okay, so this is what I get. Now, what about KCL at node 3? KCL at node 3. So of course we have V2 and V3, so we need to have two equations. Although we finally need only V2, but just writing one equation, one KCL equation is not sufficient to give us V2. So we want to write down two equations. So one equation is So one equation is the KCL at V2 and at node 2, and the other equation would be KCL at node 3. So that node equation would be V3 minus V2 divided by 2. Why? Because the current flowing out of V3 towards V2, I'm just taking one node and assuming that all the currents are flowing out. So it doesn't matter that when writing the KCL equation for node 2, I assume that the current is flowing from left to right, whereas when writing the KCL equation for node 3, I am assuming that the current is flowing from right to left. Doesn't matter, because if you see, this current is V3 minus V2 by 2, and here the current is V2 minus V3 by 2. So basically, everything is fine as long as you're consistent with whether you're assuming the current is moving in or moving out, flowing in or flowing out of some junction, and then you write the equations appropriately. So V2 V3 minus V2 by 2. Then it will be, there is a minus, then there is a 4 ampere voltage source, current source. So current 4 ampere is moving in. So whenever current is moving in, we write a negative sign, and plus a current moving out is V3 by 5. That is the current flowing out of node 3 through the 5 ohm resistor towards the ground. So that is equal to 0. So if you solve these things, you will eventually see that V3, you will be eventually able to find that V2 is equal to 200 by 87. So you make use of substitute V3 is equal to 16 by 5 V2 over in this next equation, and then you solve for V2. So your V2 would be, because V2 is all we want. We don't care about V3 actually. V3 had to be taken into account because we wanted to write a KCL equation. But in the long run, we don't care about V3. V2 is all that matters. Okay, so we have V2. So what is I2 then? I2 is nothing but V2 divided by the 10 ohm resistor. Why? Because I2 is nothing but V2 divided by V2 minus the ground potential, which is 0. V2 minus 0 divided by the resistance through which is flowing. I2 is flowing and that resistance is 10 ohms. So I have V2 by 10. So V2 divided by 10. So V2 is already, I know, 200 by 87. So I have 200 by 870. Okay. So now we see that I1 was 700 by 870. I2 is 200 by 870. So I would be I1 plus I2. So that would be 700 by 870 plus 200 by 870. And that makes for 900 by 870. And that is equal to 1.03 amperes. Okay, so this is our solution. Any questions on regarding this approach?
So,
Yes. Any questions?
sir, we can do source transformation in this, right? Like we can convert that current source to voltage source.
Yes. You could do that. So most of these
Yeah,
things, there are multiple ways. So
yeah, like we will be left with only two loops then if we convert the current to voltage source.
yes. And actually, that's a very good point. I think I made this point later in one other problem where we, as far as I can remember, there is actually another problem where we tried that source transformation as well. So we did a source transformation and we tried it. So it's actually when you're solving a problem, it's always good to see which approach is giving you the fewest number of equations. Because when you're trying to, so right now when I'm solving these equations, I'm just trying to be as elaborate as possible and then trying out all sorts of ideas. And I want to have a diverse set of techniques being used. But when you're actually solving a circuit, it makes sense to keep an eye out for different techniques and see which one is the best. So most of the time, source transformation can make it very easy when you have a current source in parallel with a resistor or a voltage source in series with a resistor, and then the entity you are looking for is suppose a voltage or suppose a current. So you can depending on whether you're looking for a voltage or a current, you can apply a source transformation and the whole problem might become much easier. So you are right, I agree with you. So you could do source transformation, which might make things a lot easier than other approaches. I agree.
Oops.
Okay, so let's go back to that video. Question. Okay, so I guess no questions. So we have solved two questions answers so far. We've gotten two answers so far, and then let's look at question number. Yeah, question number 4 is a good question to see. Question number 4 is again use superposition to find some current. So basically, we want to find use superposition, but we did the superposition previously for a circuit with only independent sources. Now in question number 4, we have a circuit that has both independent and dependent sources. So we want to find the current using superposition. So let's go to question number 4. So question number 4 is, what you have here is, you have a 15-volt source. You have a current I, a 6 ohm. This is a current 3 ampere, 3I current. You have an 8 ohms current. This 10 volts. Okay, so we have this circuit, and our job is to find I using superposition. Okay, so now to find I using superposition, again we just write I is equal to I1 plus I2. I1 is when you due to 15-volt source alone, and I2 is due to 10-volt source alone. Okay, what about a dependent source? The dependent current source, we don't need to do anything. I mean, when we're trying to deactivate some independent source, we leave the dependent sources alone. So dependent sources should never be touched. So they'll still be there. So we don't do anything with the dependent sources. We'll let them be there and solve the circuit accordingly. And whatever answer we get, we will make use of it. But for a dependent source, so although there are 3 sources here, 15 volt, 3I, and 10 volts, we need to take into account only the independent sources one by one. The independent source will always be there. So whatever we are activating or deactivating does not matter. The dependent source will be there as it is. So let's not touch it. Okay, so first let's find I1. So to find I1, so basically deactivate the 10-volt source. So what it does is, if you have deactivate the 10-volt source, you get the circuit like this. So you still have the 15-volt source over here. You still have 6 ohms. Still there is a 3I, and I is this. But now let's call I equals I1, because we are looking at not the same circuit, but just the part of the original circuit. Let's call this V1. Let's call this 8, so it's already 8 ohms. And then I just short circuit this part. So initially here was that 10-volt source. I short circuited it. So this is what I have. So now if I again write the KCL at V1, KCL at node 1, so KCL. So if I write down the KCL at node 1, KCL at node 1, and what is node 1? Node 1 is this. So if I write down the KCL at node 1, I have 15 minus V1 by 6. So that's the current moving into V1. So this time I'm saying this, moving into V1. So any current entering the node, I'll give it a negative sign.
Yes, sir. Sir.
There's a, yes.
Okay, sir. From V1 we are writing V1 minus 15 by 6.
Yeah. Okay, 15 minus V1 by 6. Okay, so here what I'm doing is I'm writing 15 minus V1 by 6. So that is the current moving towards node 1, right? Because 15 has to be a higher potential. V1 is a lower potential. That's the assumption. So 15 minus V1 is the current. 15 minus V1 by 6 is the current flowing through the 6 ohm resistor in the direction of node 1. So it's flowing into node 1. So that's why that is, I'm writing that way. And I put the minus sign because as per the convention I have been following since the very beginning. If I'm writing it on the same equation, then currents flowing into a node is negative and current flowing out of the node is positive. So if I'm writing everything on one side of the equation, so my intention is to make this one current, all these currents, so currents flowing in the 3 branches, write all of them together and they should sum to 0. In order for that to be true, I have to assign a negative sign to all the currents flowing inside, flowing into the node, and a positive sign to all the currents flowing out of the node. So that's basically the idea. So does it answer the question, or is it was it slightly different? Does that answer the question? 3I current. Okay, so let's go ahead then. So but just let me know if you have any questions. Please let me know. Then later on also we can discuss. Moving inside, moving into V1. Again, I'm making the negative sign. And then there is a current V1 by 8 moving out of V1. Okay. So here what I did was 15 minus V1 by 6 is the current moving into node 1. 3I is I1 is a current that's moving into node 1, whereas Vi by 8 is the current moving out of node 1. So that's why I said minus, minus, and then finally plus. Okay. So if I want to take the current moving into node 1 through 8 ohm, then I just make minus V1 by 8. So as I said, these directions are all arbitrary. We don't know what is actually moving in, what is moving out, but I have to be consistent in writing these equations. So if indeed the current through 6 ohm resistor is moving into V1, then that current would be 15 minus V1 by 6, not V1 by 16, 15 minus 6. So that has to be taken care of. So flowing out of V1. So that should turn out to 0. So these two currents, the first two terms are currents that are flowing into the node 1. And the third term is a current that's flowing out of node 1. So that is why we have given the signs accordingly. So if you have any questions about this sign convention, always ask me because this is important. If you mess this thing up, then final answer will always be wrong. So then, so basically what you can do is 15 minus V1 by 6 minus 3. I is nothing but 15 minus V1 by 6 again, plus V1 by 8 is 0. So you solve for V1. Finally, if you do the solving for V1, I'm just giving the final answer. V1 is equal to 240 by 19, which means that I1 is equal to V1 by 6, right? I1 is equal to 15 minus V1 by 6. 15 minus V1 by 6, right? So because we have 15 volts over here, so you have a 15 volts over at this terminal. So this terminal is 15 volts. This terminal, the terminal on the right, is your V1 volts. So 15 minus V1 divided by 6 is your current I1. So 15 minus V1 by 6. And then if you actually substitute all the numbers, so 15 minus 240 by 19 by 6, and that actually gives you, if you do it in the calculator, you'll find that it's 0.395. And then what about KCL at node 2? We don't need KCL at node, sorry. So we already got I1, so we don't care. So we don't care about anything at the about this circuit. Okay, so we have this. We use KCL to find out this I1. Now next find I2. So for I2, all you have to do is you have to deactivate the which source? 15 volt source now. 15 volt source. We will get let's call this I2 now. We have 3 I2. We're calling this node V2 now because these are different circuits actually. You are removing some parts, so that's why we are calling it a different name. So 10 volts. This right. Okay, so this is our node 2. So this is our node 2. So again, take KCL at node 2, KCL at node 2, and that gives you minus V2 by 6. Current moving in, so V2 by minus V2 by 6 plus 3 into minus V2 by 6. I'm not going to the exact discussion because it's the same as before. So just to verify that this is correct. And then if you solve this, we get V2 is equal to minus 60 by 38. So I2, what is I2? I2 is, okay, so what is I2 here? I2, we are saying that I2 is flowing in a direction left to right, which means this potential, the lower potential, the potential at the lower end of I2 or on the right end of the left end of I2 minus the potential at the right end of I2. So what is the potential at the left end of I2? That left end is actually connected to the ground. So this is always implicitly the ground. So this lower part, unless I specify where the ground is, whatever is there down below is the ground. So the ground potential is always 0. So 0 minus V2 divided by 6. So 0 minus V2 is nothing but minus V2. So I2 is nothing but 0 minus V2 divided by 6, which is minus V2 by 6. And then that would be, but V2 itself is minus 60. So basically 60 by 38 by 6, which is equal to 0.263. So now I can again invoke our superposition theorem. So the actual I is I1 plus I2, which would be these values that I wrote down. So 6, 5, 7, 8, and 6. So that's our that's the current that we were after. Okay. So any questions on this problem? Okay, then let's go ahead and solve question number 5. So what is question number 5? Question number 5 wanted us to determine the Thevenin equivalent of a circuit across some given point. So let's write that down. So question number 5. Question number 5 is find the Thevenin equivalent of the circuit. So you have a 5 ohm circuit. They're calling IX current. The independent current source is there. Then you have a 1 ohm resistor. Then you have a voltage source. It's a dependent voltage source. I just call it IX, capital IX. Let's call it capital IX. Same thing. Okay, so this is your circuit, and what we were asked to do was we wanted to find the Thevenin equivalent. Find the Thevenin equivalent across the 5 ohm resistor. What do we mean by finding the equivalent out of the 5 ohm resistor? That means if this is our output port. So basically remove the 5 ohm resistor, whatever you have, this is the output port. So I want to remove the 5 ohm resistor, whatever and end up with these two output ports, and I want to find the Thevenin equivalent with respect to that port. So to find VTH, let's first find VTH. What do I do for finding the Thevenin equivalent? The step here is to just open circuit the output. So open circuit this output. So it's the VTH here, minus 30 amperes. IX, let it be IX then, as before. One ohm. For IX. This is our circuit. This is what becomes our circuit when we open circuit these output ports. So now the question is, what about this one? What is IX? IX is 0, right? Because we have open circuited this port, so no current can flow through this open circuited port. So because IX is 0, this term will also 0. So this disappears. So this is actually becoming an eventual short circuit. So I can replace it with a short circuit. So what I have here is plus 20 volts VThevenin. So this is a plus minus. This is an open circuited point. I have this 30 amperes, 30 amps. And then I have 1 ohm. Finally, this is all short circuited. But this is nothing but this 20 ohm resistor remains the same, 20 volts, 20 volt source remains the same, but this part, 30, this whole part, 30 ohm resist, 30 ampere current, so it's a 30 ampere current in parallel with a 1 ohm resistor, right? So this is the same thing. So this is 30 ampere. So what you could do is you could use your source transformation. So source transformation says that this thing is equivalent to a same resistor in series with a 30 volt source. Why 30 volts? Because 30 times 1 ohm, 30 amperes times 1 ohm is 30 volts. So 30 volts. So these two are equivalent. So these two, this is a source transformation. So what we do is we do a source transformation to write down 30 volts. So we basically what we did was we transformed the source. So this is source transformation. Okay, so once we do the source transformation, we get this. And so this can be simplified further because if you look at this circuit, you have 120 volt and another 30 volt in series, and their potentials are the same thing. So there is a potential. Yeah, so if you move in this direction, so if you move in this direction, so there's a potential rise. So when you move from this point to this point, you have a 30 volt potential rise, and then you go ahead, and then you have another 20 volt potential rise. So that's a 50 volts rise. So we have a 50 volts. This is VTH. Okay, so this means your VTH is nothing but 50 volts. And then there is a 1 ohm, sorry, I forgot 1 ohm. Okay, so 50 volts. So this is your Thevenin voltage. Is this clear to everyone, how I found the Thevenin voltage? I mean, I use source transformation. You could use something else. You could do nodal analysis, mesh analysis, KCL, KVL, whatever you want. Doesn't matter. But this one, source transformation, seems like the best way to deal with. Whenever you see a current source in parallel with a voltage source and parallel with a resistor, and you are trying to find some voltage, always think about source transformation. Oftentimes, source transformation is very useful. And then finally, I need to find RTH. Okay. So let's hope everyone's happy with the way we found the VTH. Now we need to find RTH. So again, we have the same circuit. For RTH, what we need to do? So we need to go back to the circuit Across these output ports, in this case, again, this output port is actually A and B. Suppose across A and B, what I'm going to do is I am going to put a test voltage, test source. Why test source? Because there is a dependent source in here. So because there is a dependent source, I'm just going to put some test source with, let's suppose we put a test voltage with some voltage Vt. And then we will solve for the current, whatever current this voltage source is inducing. So that voltage divided by that current, with the input voltage divided by the input current would be your Thevenin resistance. So basically what would happen here is that, and also as I already did mention, when you are doing this test voltage method, you will have to deactivate all your independent sources. So all you have to do is you just connect this point, so these 2 points, so this A, B points where there was originally the where there was originally a resistor. There I am putting a voltage source across this output. Then there was a current source that's disconnected. So this was the originally current source was there, but there was a current source in here. So I removed the disconnected current source because I want to deactivate it. Then there was this 1 ohm resistor, it's as it is. And then there is this dependent voltage source which should remain here, Ix, okay? So I have a current Ix here, Ix. So what we claim is that we connect a voltage, test voltage, and that test voltage will create some current, IT test current. And I eventually want to find out the ratio of the test voltage by the test current. Okay, this is what I want. Now this test current in this case is just the same as this Ix. Ix was a term that was defined in the original question. So Ix is the same. And then, which means that this voltage is for Ix is nothing but for IT. Okay, so I have this circuit now. And where did this part come from? This was the disconnected current source. I deactivated the current source, the independent current source, by open circuiting it. And here there was a voltage source, which I deactivated by short circuiting it. So I get all these things. So now let's write down the KVL equation. So here KCL doesn't make any sense. We have just one loop. So the best thing to do here is to write the KVL equation. What does KVL equation say? If you sum up the voltages across the loop, they should all sum to 0. So basically, I start from the point A. Suppose I start from here, and then I move along the loop. So as I move from A to B, I have a voltage rise of Vt. Then as I move this direction, there's a current IT flowing through this 1 ohm resistor. So there's a voltage drop of IT times 1. So there's a voltage drop of IT times 1. 1 is from 1 ohm. And then as I move in this direction further, there's another further voltage drop of 4 IT. Okay, one minus, there's another voltage drop of 4 IT. And that should all lead to 0. So this is the KVL equation. So when I write the KVL equation, I get that Vt is equal to 5 IT. So Vt by IT is 5, which means R Thevenin is 5 ohms. Okay, so this is the way you find R Thevenin. Okay, so we actually solved another problem in the previous lecture, the problem number 6, but in this case we are already out of time. So what I would do is I will cover that problem in our next meeting. Okay, so we have covered today question number 1, 3, 4, and 5. So 6 will be covered later, but just for your information, that was already covered in the other tutorial session for the SMS and SMME section. Okay, so because you have another class, I will let you go now. So we will meet for our next class. I think it's tomorrow, I guess. Okay. All right. So see you tomorrow.
Thank you.
Okay.